This is part 2 of the stoichiometry video. We just finished talking about the s'mores example, and now we're going to move on to example 2 with a real chemistry equation. So we have this chemical equation. It says balance the equation, then use appropriate mole ratios to find the theoretical yield in grams of calcium phosphate. So let's start by balancing the chemical equation, and then that will become clearer of what our mole ratios will need to be. So looking at this equation, it looks like pick an element that's not balanced. We've got phosphate. Let's put a 2 there, and that makes our sodium 6. I'm going to put a 6 here. And then if I make this a 3, now my chlorines are 6. And that would be a 1. So 2, 3, 1, 6. Again, if you are, if you prefer to make a table and count the atoms, feel free to do that while balancing. So now let's actually use this. And remember, in part 1, we talked about how these coefficients are going to represent the amount of our reactants and products that form together in these particular ratios to make our products and our reactants. So we can say that they are really equal to each other and use them as conversion factors to move from one compound to another. So I'm going to show you in this part 2 video how to use mole ratios as a conversion factor. So our given here in this problem says if 0.42 moles of sodium phosphate, let's write that, Na3PO4, there's our chemical formula. If that's going to react completely, what mass of calcium phosphate, that would be this guy, A3PO42. So we want to know what mass, it's grams, will be produced. Okay, so notice we have 2 different compounds, and we have never converted to a different compound before because we haven't had a relationship to relate them. We've only been able to do changes from moles to grams, or moles to liters, or to molecules of one type of compound. But when we have a balanced equation, we can use mole ratios to change the compound. So if I start my little conversion train tracks here, Na3PO4, okay, there's my given. I need quite a few steps here, so it might spill into my answer box. Since my given is already in moles, I can go right to the mole ratio to compare the relationship between sodium phosphate and calcium phosphate. I'm going to circle our numbers here that go with each of these. So I've got my coefficients. This is telling me that for every 2 moles of sodium phosphate used, I will be producing 1 mole of calcium phosphate, assuming that the rest of the reactants are available. Kind of like we did in part 1, where we did this problem here and said, well, it would make this many for this reactant, this many, and so on. That's kind of what we're doing here. Looking at the reactant of Na3PO4 to find out how much will be produced. So I can use this as a relationship between my 2. We call this the mole ratio. So I'm going to use the 2 from my coefficient. 2 moles of sodium phosphate for every 1 mole of calcium phosphate. And these are coming straight from my coefficients. Whatever those numbers are, that's what goes in your mole ratio. Then I need to convert to grams for my find product because our unit here is grams. And just like we learned previously, if we're going from moles to grams, we can use the conversion factor of molar mass. I'm going to write my work over here to find molar mass. So if you have a periodic table handy, go ahead and pull that up. we have 3 calciums, we have 2 phosphorus, and we have 8 oxygen. Pop that in your calculator, we get 310.18 grams. There's our molar mass. Grams in 1 mole of calcium phosphate. Okay, so now we have all of our work done. And again, just to clarify, this middle step right here is the mole ratio using the coefficients as that conversion factor. Let's pop this in our calculator, and I get 65 point, I think your calculator will say 138. But our given had 2 significant figures, so my answer is going to be 65 grams of calcium phosphate. Final answer there. There's how you use a mole ratio from those coefficients. That's our final conversion factor here. So you have some examples to practice that using the stoichiometry practice on page 4. And some of them you are just going to do, one step using a mole ratio. Others you will also need to use molar mass or molar volume to get to the needed unit. I think most of these are going to use molar mass if it isn't just moles. Now, I wanted to clarify on page 5, it says map out the conversion factors needed to solve each step of the following calculations, but you do not need to actually solve these. You just need to map it out. So what I mean by that is tell me what conversion factors you will be using in each step to be able to convert properly. So your 4 conversion factor possibilities are molar mass, that's the first one we learned. That's grams in a mole. Molar volume, that's liters in a mole. It's 22.4. It's a constant value. And Avogadro's number, which are the number of atoms or molecules, 6.02 times 10 to the 23rd power in 1 mole. Those are the 3 we learned last week. And our 4th conversion factor now is the mole ratio using balanced chemical equations. So for number 1, and for all of these, start with your given, and then draw an arrow. And I want you to write above the arrow which conversion factor you would use. Since grams are involved here, this would be molar mass of magnesium, since that's the compound we are working with. And if we use molar mass, that will get us to moles of magnesium. Okay. But our question wants us to have moles of Mg3P2, which is a different compound. So we will need to use a mole ratio to change from one compound to the other, and then that will give us our moles of magnesium phosphide. So there's your map, okay? The most that you'll have to do are 3 arrows because generally the process is 1, get to moles. So that's what we did here, get to moles. Then use a mole ratio to convert moles to moles of a different compound. And then get to whatever the find is. In this case, it was already moles, so it was only 2 arrows. But in other cases, maybe you're finding grams, you might need to use the molar mass of that compound. Or maybe it wants you to find liters, and you might need to use 22.4. So again, 3 arrows are the most you'll need. If it gives you moles and you're finding moles, then all you'll need is 1 arrow of a mole ratio. So you'll have 1, 2, or 3 arrows, those little relationships that are representing your conversion factors. Again, you do not need to actually solve these. I just want you to go through and map out what you would do to solve it. Now, if you would like to get a little extra points, you can definitely solve them if you have extra time to do that. So the problem for this one needs a balanced equation because it does not have one provided. So I'm going to write that for you. Here. Okay, the balanced equation is, oops. 3 magnesium, 2 hydrogen phosphide, magnesium phosphide, and 3 hydrogen. So if you would like to solve these for extra points and you have extra time, go for it. Here's your balanced equation to help you with those mole ratios, because you'll have to have that. Otherwise, you won't have coefficients to make a mole ratio. So there's 6 problems there. And then running out of ingredients is similar to that concept we used with the s'mores, but this time with burgers, just to help you reinforce the concept of a limiting reactant.